Okay, we're ready to go. Good morning, everybody. There's a reminder on the screen, Chris. Good morning, everybody. Oh, we're gone. There we are. All right, welcome back. Week 4, Advanced Hydronics. My name is Jim DePalma. With me today, riding shotgun, answering the questions, is Mr. Robert Clemens. Running the board, as always, is Christy Ann Levine. And Mr. Brett in the background, all right, our Director of Marketing. So I need you guys all to make me look good today because today is week 4. Today we are going to do a lot of troubleshooting. We are also going to have a grand review of what we've covered from the first 3 weeks. Chris, I need control, please. Okay. All right, so everybody, if you don't recall, on your screen where the 3 hash marks are, you can make me larger or smaller. You can make the presentation as big as you want. On your left-hand side is your question box where you can type in your questions. Rob will answer them, and if there's good questions for the group, he will let me know, and we will discuss them. All right? We have a lot to cover today. Please make sure. Oh, Rob, I need a Takeout Catalog. I forgot to grab one. Make sure you have your downloads, all right, that are available for you. You're going to need your Takeout Catalog with the pump curves and the different pipe sizes and what have you. So, any questions from last week when Johnny presented week 3 and we started to have more troubleshooting? Yeah, we could use that one.
Actually, that's probably the other one. Yeah.
All right, as we're scrambling for a Takeout Catalog because I'm unprepared, but shame on me. There we go. There we go. Thank you, sir.
You got it.
All right, so make sure you have your download of your Takeout Catalog. So, Robbie, any questions from last week?
Nothing yet.
Nothing yet. Okay. So we're going to motor forward. So this is what we're going to cover today. We're going to do a review of weeks 1, 2, and 3, just to make sure everybody is remembering what we've covered. We're going to go over switching relays because as you start to build these systems, we do have to control them, which seems to be sometimes a question as to how do I do this? How do I have multiple temperatures? How do I have multiple pumps? How do I do multiple pumps and multiple zone valves? And we have some really good solutions for you with our Takeout switching relays. And then from there, it's time to put everything that we've learned over these past 3 weeks into action. We're going to have some root cause troubleshooting. We're going to present you with some problems, and you guys got to figure it out. Okay? So first things first, I do want to show you something new that's coming from Takeout. All right? This is brand spanking new. Takeout's been working on this for a while, and it's kind of where the industry is going. This is air-to-water heat pumps. This is a whole package unit. As you can see on the screen there, it's got a pretty good look, but it's large. I mean, because it's air-to-water. We need a lot of surface area to capture that energy that's out in the air. But this would be a package unit that will make heating and cooling and domestic hot water. So here's the whole outdoor unit completely set up for you with the heat exchangers. You can see large fan, control box, the compressor, which is inverter driven, so it's going to be highly efficient. We have a heat exchanger, that's the water to refrigeration heat exchanger, and then your pipe connections to the indoors, you can see right there. Indoor unit, again, is completely set up for you, all inside in a nice box, pre-assembled. What do you get inside? All right, we're going to show you that in a second, but this will reduce, we feel, at least 50% of the installation time when it comes to setting up a system like this. So I could actually be replacing a boiler and go in with a system like this, depending on what we need in BTUs. So here's what's inside the box. You can see we've got 6 shut-off valves, 2 different ECM circulators, 34E, so they have a wide range when it comes to GPM and head. Nice easy wiring hub, which is internet ready. All right, so this could be monitored from a distance, and also you can change things from a distance. You're going to get the expansion tank inside it, air separator, Sorry, folks, we may have lost audio.
I changed it to the meeting.
Okay. All right, so I think we're back. I'm sorry we lost audio there for a second. So in that buffer tank, there's also an immersion heater. So if we have to maintain tank temperature, and if we can't get enough energy from the outdoor air, we could do it that way. And how does it pipe up? What does it look like? Well, here's a cool picture. Chris, I need control again, please. So there's the outdoor unit. We got 2 pipes from the outdoor unit going into the indoor, all right? And then we have our piping going out to our system. And then we have our piping going out to our indirect. So the connections are going to be pretty simple. The hydronics don't change. Everything we've learned so far in our advanced 4-week training class apply. So if you want to set it up as a zone valve system, all right, single pump going out to the system side, space heating for the home with zone valves, we could do that. And to make domestic hot water, you could do a zone pump system if you need. And some other piping schematics just to show you where we're coming in from the heat pump from outdoor, going back and forth into the system, and also going back and forth from the domestic hot water tank. All right, and you can see the element. So I'm not going into great detail here. I'm just showing you where the future is, and this is going to be available come the fall, I'm told. What kind of performance are you going to see? Well, at 47 degrees outdoor air, based on those different water temperatures, you can see that we can get up to 32,000 and change on the BTU side if you need 140 degree water. And if you've been following us with our webinars, again, Anthony Tassi did a really good webinar on low temperature systems. And if I'm designing a system from scratch or maybe retrofitting a system, and I could take advantage of the extra baseboard that's in the system, and if 140 degrees will be adequate enough to heat the building, then I can get away with that, all right? And you can see I'll get that 32,000 BTUs. And then if we get to 17 degrees outside, which is very close to our average coldest day of the year, right around here, at that 140 degrees, you can see it drops down to 22,985. So you may need some backup, maybe an electric boiler, or maybe the immersion element will be enough to keep the tank at temperature. So this is where we're going. This is the future. This is where things are going to be. So I just wanted to get you guys a little excited about that. This is stuff that we're going to see down the road from Takeout. All right. You ready, Rob?
Yep, I'm ready.
You don't sound very enthusiastic. Are you ready, Rob?
Yeah, I'm ready. Are you ready?
I'm very ready. I don't think he was very enthusiastic, Chris. All right, let's get going. All right, first thing first, the most important thing we learned in our classes was the universal hydronics formula. We use this every day to size our pumps. Everything we need is going to come from this formula. GPM is gallons per minute. BTU is the load. Where do we get the load from? We get the load or the actual BTU content that the appliance is going to provide. Delta T is our design temperature difference, 20 for baseboard, or as we say, high temperature systems, 10 degrees for radiant. They also could be 20 degrees. They will also be 25 degrees. And remember, 500, that's the only number that is consistent throughout the whole universal hydronics formula. Where did that come from? The weight of 1 gallon of water being 8.33 pounds times 60 minutes times 1 degree. We're raising that gallon of water 1 degree over 60 minutes. You math that out, you get 499.99, 500. So that would be your consistent number. So we can figure out GPM by this formula. And if we, instead of dividing by said 10,000, say multiplying by 10,000, we can take a GPM and turn that into a BTU. And a little note to self, you're going to be doing that a little later when we get to our troubleshooting. So if you want to, Chris, can I have control, please? If you want to take a screenshot of this, here we broke it down for you, where if it was going to be a 10-degree delta, you end up dividing the BTUs by 5,000. If it's a 20, it's by 10,000. If it's a 25, it's by 12,500. If it's a 30, it's by 15,000, and if it's a 40, it would be by 20,000. So if you want to do the math yourself, great, or take a screenshot here and save it for future use. This is a really good information here. So once we know GPM, then we can figure out pipe size. Once we know pipe size, then we can also make sure that we're going to maintain good heat transfer by making sure we don't go too crazy by putting too much baseboard on a loop. So you can see based on pipe size, half copper, no more than 25 feet. All right, 3/4 copper, no more than 67 feet of baseboard. So don't go crazy with a 3/4 loop on baseboard and do 70 or 80 feet. End of that loop is going to be too cool to really transfer any heat. Rob is really paying attention to this when he's into that, right? So as you can see here, this is based on 180 degree. We give it less water temperature, and we'll have less baseboard on that loop or lower output coming from that loop. BTU capacity of copper pipe and iron pipe. So based on these flow rates, those average flow rates, which is what we have talked about over these past few weeks. All right, 2 GPM, 4 GPM, 8 GPM, 14. Those pipe size of half, 3/4, 1 inch, 1.25 inch, the very common pipe sizes that we use in our systems. Based on that 20-degree delta, you can see the GPMs that we recommend that we don't cause any problems by causing any velocity noise or erosion. You know, if I'm going to move 4 GPM through 3/4 copper, I should equate that to 40,000 BTUs. As we make the delta T larger, you can see that the BTUs actually get larger too. So if you can design your system for a larger delta T, we can actually move more BTUs. Take a picture of this screenshot. All right, this is good information to have. All right, moving forward. So with all that, we want to size our piping. So we want to stay within these GPM ranges for these size pipes. Again, not to cause any noise or erosion. We want to make sure we're not going over 4 feet per second. If you've ever been on a job where they were moving the water faster than that, it could cause some tremendous amount of noise. It could sound like a rushing river, and that could be because we've got some air in there too. But if we're moving the water really fast and the pipe touches a structure within the building, it could sound like a train coming through the building. So we want to make sure that we don't go over these velocities, and we want to make sure that we don't go under 2 feet per second, because then the air bubbles in the water get big, fat, and belligerent, and they're difficult to remove. So these are tried and true GPMs. This is where we stay, and this is how we have really good performing systems. Now that's based on copper pipe, iron pipe. In your handout from your Takeout Catalog, you also had a PEX chart there, and you'll see that the GPM through the piping on PEX is different because the resistance will be different, because the internal diameter of PEX pipe is smaller than copper. So we do have to be very cognizant of that. We don't want to force high GPM at a high velocity through pipe to make up a BTU difference if it's PEX, because we can erode it. Remember, it is plastic. All right. So what we're showing you here on this chart is if you start to get into the gray areas, you're moving too much water through that pipe. You need to upsize the pipe. And I just want to point out on the chart, especially under 3/4, where 4 GPM, where is it? Right there, we're looking at 0.11 as the pressure drop per foot. All right, 0.11. So that 100-foot loop of copper with our head loss formula, that always turns out to be 6 feet. In the world of PEX, 100 foot of 3/4 PEX, that would be 11 feet of head. So you have to be very aware of that. Don't undersize your PEX pipe, or don't size it like it's copper. It's going to lead into some issues for you down the road. So velocity is important. We don't want to go above 4, and we don't want to go below 2 feet per second. Kind of doing a speed date here because I really want to get to a lot of information today. Any questions so far here, Rob?
Not yet.
Nothing yet. All right. Another really cool formula that John showed you guys was indirect hot water recovery time, or recovery time for any domestic hot water, where we're taking the gallons times the domestic delta T. And again, there's your consistent 500, and we're dividing that by the BTUs of our appliance. So here we're showing you an example of a 40-gallon indirect. Where does the 36 come from? That's the available gallons in that tank, because the coil is taking up some space inside the tank. Where did the 115 come from? That's the actual supply water temperature we want to deliver out of this indirect. So if you want to make that 120, you can change that to whatever you want. Where does the 50 come from? The 50 comes from as our average incoming water temperature. If we have a really, really cold winter in this territory, it can drop down to 40, but on average, we'll have 50-degree coming in. We do the math inside the parenthesis there first, and then we're going to multiply these numbers by that consistent 500, and then divide it by a BTU. So in this example, we're using 100,000. So that's where the 36 comes from, times 65. That's your difference between 115 minus 50, times 500. We divide that by 100,000, and what you end up getting is 11.7. So this 40-gallon indirect will recover in 11.7 minutes. Great formula to have. Write that down. Take a screenshot of that if you can. That'll help you in a lot of jobs where they complain of insufficient hot water. All right, at least you can get an idea of how fast the appliance is recovering, and then compare it to the actual usage of the homeowner, and then come to your resolution. Okay? Rob just took a picture of it himself. All right. Cast iron boiler systems. They're out there. They've been around forever. They're workhorses. Not a lot of maintenance required. Can you make them more efficient today? Yes, you can, by using our ECM circulators, either variable speed ECMs that will change speed based on pressure differential, or by temperature. I happen to use the temperature one on my cast iron system at home. Makes a big difference in the comfort of my system. Looking at this screenshot here, there's 3 circulators. Yeah, I can make them ECMs. I don't need the extra separate flow checks. If we need flow checks, we can get them now where we put it right on the circulator. So it'll actually have the circulator perform better. You'll see that there's mix valves there. Those are standard mix valves, or static, as I like to say. That means I'm always going to get the same temperature out of it at all times. But we learned that doing a heat loss, when we do our heat loss, it's based on the coldest day of the year, and the temperature outside changes all season long. So that means our BTU requirement to heat the home will change on a daily basis. And if I change the mix valves into a mix valve that can change its output based on outdoor temperature, again, I make a much more efficient system and a more comfortable system. So things to take into account when I'm looking at, say, a young cast iron system that could be 10 to 15 years old. Customer says, you know, can I upgrade this? Can I make it better? And the answer is yes, you can do that. And if you got questions about that, contact us. We'll help you. We'll give you some good ideas on what to do. Then we've got our condensing boilers. We talked about condensing boilers, again, in that low temperature class in great detail. Earlier in our advanced 4 weeks, we talked about it. What's the difference here? Well, they condense, obviously, and we want to make sure they're going to run in condensing mode. That means my return water temperature has to be at least 130 degrees to start the condensing. And as the water gets even colder and colder, we condense more and our efficiency goes up. You see these come as combis and as heat only. If it's a combi, that means it's going to have a heat exchanger inside it to make domestic hot water. Do not oversize the combi to meet a large domestic demand. All right, if your domestic demand is very large or larger than the space heating requirement, you probably want to have an indirect for that domestic hot water, or possibly a whole separate appliance just to make domestic hot water. We see too many combi units go in where they oversized on the combi side for domestic, and then we end up short cycling dramatically on the space heating side. So try to get these jobs as tight as you can. And again, if the domestic load is so much higher than the space heating load, we should address that separately. The other important things with these boilers is venting them properly, using the proper material to vent. Remember, whatever your space heating load is, whatever your water temperature is going out to your system, your flue temperature will be 20 degrees higher. So if a majority of the time this boiler is making above 150 degrees, your flue gas temperature will be at least 170 or higher. You are well out of the range of PVC pipe, all right? You cannot use PVC pipe if you're going to go past stack temperatures of 140 degrees. That would mean you're supplying 120 as your supply water temperature. You have to be very aware of that because you'll start to break down the PVC, and it doesn't take long for that to cause an issue. In less than about 9-10 years, we can have a catastrophic failure. We don't want to see anything like that. You want to use the proper material. All right, we represent Centrotherm, which is a poly pipe, which is made exclusively for venting. That's what it's for. It's not a drainage pipe. That can handle temperatures up to 230 degrees. And remember, to get that 230 degree rating, it has to be able to handle 300 degrees. So a material like that, as you're venting, will be safe and you'll be in good shape when you're putting in these type of systems. Okay? Venting is really, really critical with these boilers because a lot of times maybe you cannot use the actual chimney as a chase. You have to come out the side of the building. You want to make sure that you're using the proper material and you space the air intake away from the exhaust. Any questions on that, contact us. We will help you out. Why is it important to make these boilers condense? Is because of all the BTUs in that condensate. That's what we're trying to recapture and absorb back into the boiler. 1 gallon of condensate will give you 8,080 BTUs that if I don't recapture, just end up going out the stack, out the vent piping, and now my boiler is not going to achieve that 90 and 95% efficiencies. Okay? So again, if we're doing condensing, we want to make it condense as much as possible to get that efficiency. Why is that important? Because of our degree days. So if you're looking at this chart, which we've showed you before, a majority of the time, 60% of the time 49 days or 26% of the time, I only need 60% capacity out of the boiler. Okay? All right, what does it say there? 35% of the time, I only need 40% capacity out of the boiler. Thank you, Chris. So, guys, we do our heat loss based on the average coldness, the worst case scenario, but a majority of the time, we're not there. So that's why doing that heat loss, what we did week 2, really dialing it in to get as tight as we can to the actual BTU requirements of the job is important. Okay? Very important. Taking advantage of that heat loss then helps us figure out what we could do with existing baseboard, or if I'm going to design a job from scratch, can I use regular baseboard and use lower temperatures? So we're showing you here, every manufacturer for baseboard will give you a chart that'll show you based on input of the supply water temperature, what BTUs you'll get per foot out of the baseboard. So generally everybody looks at baseboard and says, okay, 180 all the time. You want to focus on the 1 GPM side of the chart. That would still be on the conservative side. And depending on the chart, you'll see 550, 580, some say 600. It's really about 580, and your average water temp supply is probably going to be about 570. But if I've got more baseboard on the job than I need, and how did I figure that out, Rob? Because I did the heat loss. So the example that I used was my own home. I had twice the amount of board in my house that I actually needed. 150 degrees would suit my purposes, even on the average coldest day of the year. And as you can see, if it was the Petite 7 at 150, it's going to give me 390 a foot. And on bottom, I think that is slant fin. And at 150, it's going to give me 350 a foot. Okay? So knowing that based off of my heat loss, that can make sure I can make sure I'm going to heat the home properly. Okay? So use these ratings to your advantage. We talked about primary, secondary piping. That was the other important difference between a cast iron install and a condensing boiler, is how they pipe up. All right, we have to do primary, secondary on condensing boiler systems because I'm going to have a different flow rate for the boiler versus what I'm going to have on the system side. And the reason why we do primary, secondary is to separate those two flow rates. The circulator on the boiler and the circulator or circulators on the space heating side or system side never see each other. So closely spaced T's, right? Thumbs up, put your knuckles together. That's a closely spaced T. It's as simple as that. Or you can buy a low loss header, a pre-made closely spaced T, and that separates, hydraulically separates the two flow rates from each other. So we went over that in detail. We went over showing you if you're going to do a multi-boiler system, how we can do closely spaced T's and connect to the main. And here we're showing you actually a primary, secondary with reverse return. So you can see on the bottom there, the first boiler on the right-hand side is the first boiler into the T, but it's the last boiler out on the return. So this will then enable us to have equal flow rate across the three boilers. And why would we do this on a multi-boiler system? Well, these are condensing. What we're probably going to end up doing is set it up that as the first boiler is firing, and if it needs to fire to a higher temperature, we want to then turn on the second boiler to make sure I don't take the first boiler out of condensing mode. We'll fire the second boiler up, still keeping it within its condensing mode. Then if I even need more BTUs, we would fire the third boiler up. So if all three boilers here would be firing, they'd still each be in their condensing mode, and we would be delivering enough BTUs to the system. Systems like this, we always recommend you prefab your closely spaced T's, all right, maybe even part of the supply header that's going to the system. This way you can come into the job, mount it on the wall, reconnect to what's there on the job, and then set your boilers up. Okay? Any questions on that? Okay. All right. So that is my speed date on review of what we've covered over the first 3 weeks. Now I want to get into how we would control some of the jobs that you're going to be laying out there. So I want to go over our Takeout relays, our SR panels, and our ZVC panels. SR panels, switching relay, this will cover if we're going to do multiple pumps or even a single pump. And ZVC, zone valve control, if I'm doing multiple zone valves. And that control will also handle multiple pumps too. Makes wiring up these jobs very, very simple. We do a low voltage wiring class that is based around these relays. So if you're interested, contact us. We can always do that webinar for you or live. But what happens is we can now take a young tech or somebody who's not comfortable with the low voltage side of the system or the control side of the system, introduce them to these products, show them how to use it, and now they're wiring up the systems on their own. They understand how the system's going to operate. They have more control, and it's going to help on the troubleshooting side also. So let's get right into it. So here I'm showing you our SR 504, 506 switching relays and connecting to a typical boiler control, okay? So this is for zone pumping. So if I'm going to zone with pumps, this is a multi-switching relay where I can have up to 5 or 6 pumps per zone. With our expandables, we can go out to, I think it's 100 pumps, 120 pumps. And so I'm going to show you how we wire it up. So first things first, we have to bring in power. So you're going to have from your circuit panel, you're going to have all these different switches. All right, the customer emergency switch, that's the one that should be at the top of the stairs. all right? Service switch is probably going to be right at the boiler, and then you're going to have low water cutoff. So on my mock-ups back here, we're showing low water cutoffs that are 120 volts. So the low water cutoff will operate as a switch. Has to be above the boiler to make sure that there's water above, so the whole boiler is filled with water. And if we had no water at the low water cutoff, we would cut off power completely to the system, so nothing would be powered. And that's a safety switch. So after going through the low water cutoff, we come into one side of our 120 volt input. So that is our incoming power. All right. You see a dot on the screen, and the wire continues on to L1 on the boiler relay control. That dot basically is a wire nut. So we're bringing that incoming voltage to L1. Then what do I have here? I have my white neutral. You're going to see another dot, the wire nut, bringing the neutral to L2 on the boiler control itself. That's how we bring our incoming power in. So far, so good. This should be pretty simple. What's next? It's going to be our thermostats. So this is an older screenshot here. We do have an R, W, and C now for our thermostats on these SR panels. C would be the common. So if you need a digital stat that needs constant power, we have that off of the relay panel. So here we're just showing you a 2-wire install. So R and W, no big deal. We run our thermostats to the top. Okay, what would be next? Now I'm going to power up my pumps per zone. Very, very simple, just 2 wires. Okay, what's next? I've got an end switch coming out of this control. So if any of these thermostats call, thermostat's going to close on a temperature fall. It's going to now energize that circulator for that zone. We will then close the end switch contact on the SR panel, which then goes to TT on the boiler, and that's going to end up firing our boiler. And then if I'm also now going to have the boiler control the circulator on the boiler, it would close that contact within its own little relay and end up turning on the boiler. All right. Pretty simple, Robbie. Can you wire this up?
Easily.
Brett's going to wire one up tomorrow. He's so excited by this. Any questions on that? Pretty cut and dry, pretty simple. Looking good? All right, Chris, you're next because you're going to do the zone valve controller. So our zone valve controller is going to follow the same thing, except we're going to be using zone valves, but I have the opportunity to drive 3 different circulators on this system if I choose. So again, we're going to bring our incoming power in from the circuit breaker itself through the emergency switches, again through the low water cutoff is my last safety. Highly recommend the 120 volt. And you can see now we go to 2 transformers. In these ZVC panels, we give you 2 transformers because we split the panel in half. So 1 transformer is taking care of the first 3 zones on this 406, and the other transformer is taking care of the next 3 zones. So I always give you enough volt amps or VA based on whatever zone valves or thermostats you're going to use. So this is the incoming power, all right? And then I've got my neutral, so I got the same thing there. So again, when you see the dot, that's a wire nut. So now I've brought power into the panel. Next, I'm going to take my thermostats, and this is R, W, and C. All right, so we're just going to be using 2 wire here. My last zone is my priority zone, so that could be a thermostat if I'm not going to have a priority for domestic hot water. But if I am going to have an indirect tank, all right, I can just take my aquastat and wire it to the last zone. And there's a priority switch right on the panel itself, so if I put that in the on position, now my domestic is prioritized. So now what's next? I've got different zone valves. So I can do a 2-wire, I can do a 3-terminal, or I can do a standard 4-wire on the bottom. Because where my zone valves wire up, we give you 1, 2, 3, and 4 terminal. So the number 1 terminal, number 2 terminal, those would be your yellow wires, all right, or your motor. And then the 3 and 4 terminal is the end switch. So if you're using a 2-wire zone valve, Robbie, when was the last time you used a 2-wire zone valve? Probably never.
Yeah, I don't recall ever using one.
Probably never, but we use them today all the time. And where you're using them on radiant systems. Those are the actuators. Most of them today are 2-wire, because all we're going to do is energize the motor to open up the actuator, all right, to power and open up the valve. So if you're going to use a actuator or a 2-wire zone valve on this particular panel, we're asking you or showing you to put a jumper across 3 and 4, because we have to tell the panel that the end switch is closed. And that information is right on the inside cover of the panel. These wiring diagrams are right on the inside cover of the panel. So we're showing you this even when you open up the package and you're looking at it. The 3-terminal, that would be my Takeout 570 series, 570 to 571. And those are 3-terminal, but they are 4-wire zone valves. 1 and 2 is motor, 2 and 3 is end switch, 2 is the common terminal. But when we wire it up to our panel, it's simple. 1 goes to 1, 2 goes to 2, 3 goes to 3. You're done there. And then we're showing you a 4-wire configuration. Anybody's 4-wire zone valve works. So your standard Honeywell, your 2 yellows go to 1 and 2. Your 2 reds go to 3 and 4. Remember, 2 yellows are the motor. That's your 24 volt. The 2 reds are your end switch. If it's the Takeout Zone Century, we don't give you wires. We give you the wiring harnesses. We want you to use standard thermostat wire. And we label on the harness 24 volts, and we label on the other harness end switch. All right, so easy to wire up anybody's zone valves. Then on the left-hand side, the lower left-hand side, right down here, we give you what's called dry contacts. Those are switches that are either in normally open or normally closed position. If you're not familiar with that, those terms mean, normally open means the switch is sitting there in an open position, and when powered, would close. If it's a normally closed switch, it's sitting there in a closed position, and generally when powered is going to open. And we give you those switches there so you can now run different circulators. I give you the option of running a system circulator, a domestic circulator for domestic hot water, or what we call a secondary circulator or your zoning circulator. So if we're going to use all 3 of them, this is how we connect them up. I need more coffee, damn it. So we come out of our end switch there on the panel, we go to TT on the boiler, and now it's time to wire up our circulators. So I have to bring power into these switches because they're dry. There is no power there. So I'm going to take from my incoming power at that wire nut, bring the black wire in, and that's going to go into the main pump end switch, which is a normally open switch. Then I'm going to come out of there, and I'm going to go over into the common terminal. All right, so I'm coming out of that. I'm going to the common terminal, and I'm also going directly to the system circulator. This is incoming power. Then coming out of the normally open switch, I'm going to my domestic pump. And then coming out of my normally closed switch, again, this is power, I'm going to my secondary or my system or zone pump. Okay? And then we have the neutral side coming from each pump back to the power that's coming in. So what will happen here, if any of these zones call, any of the zones call for space heating, the normally open switch at the main pump end switch closes. So that circulator will always come on. All right? But then that power is going to come out of that closed switch, go into common, and the normally closed switch is going to stay closed, and that would power the secondary or your zoning pump. Then if there was a call for domestic hot water, what would happen is the normally open switch for the main pump end switch will close. So that circulator will run. But the normally closed switch for the zone pump is going to open. And then a normally open switch that's connected to the domestic hot water pump will close. So in this configuration, I'm always going to be driving 2 circulators. your choice how you pipe up the system. If you don't have to have a main pump come on, all right, depending on how you're piping up the system, I can just have power come into the normally open main pump end switch and come out and not connect it to a circulator and just run the secondary or zone pump and just run a domestic pump. All depends on how you pipe up the system, okay? Now, the other cool thing about these panels are lights. So on my SR panel, I give you one power light, which is the green light, which should always be lit. And then if any of the zones call, you'll see a red light to show you that that zone is calling. Simple. On the zone valve, I give you the same green light to show power, but then every zone gets two lights. So if there's a call for heat, meaning that the thermostat closed, I'll get a yellow light. And then when the zone valve actually opens, right, it opens and it makes its end switch, I'll get a red light. So those lights, as I always like to joke around, they're not there for entertainment, they're troubleshooting. So if you had a problem on the job, you show up at midnight and there's, a problem, you've got no heat in a room or two, and you go downstairs and you see the green light, well, you've already figured out that you've got power to your boiler, to your system, to your control. And then if you see that, oh yeah, the third zone's not working because I got the yellow light, but I'm not seeing the red light. So I'm getting my call for heat, that's the yellow, but I'm not making my red light. That means I'm not making the end switch. I've got a bad zone valve. And I can, remedy the problem quickly. So this is really good. Makes any B tech or C tech much more comfortable when it comes to low voltage wiring. No offense to any electricians out there, but we don't need you here. We just need the electrician to bring power to the board, and then from there we can wire it up ourselves. I can daisy chain these guys out with my expandable panels up to 120 zones. So I get that big job. There's a job that came across my desk. Small house, Brett, it's only 30,000 square feet.
That's it?
Only 30,000, yeah. So we're going to be redoing that system. So there's going to be a lot of zones there. We're going to do it with these EVC panels, all right, and SR panels. So it'll be quite simple to do. Robbie, any questions on that?
No, it's everybody seems
All right.
to be
We're
taking
killing
this
them
well.
today. Good. All right, so if I do have an aquastat and a domestic pump for my indirect on this particular job, the instructions will tell you to put a jumper across the 3 and 4 terminal on the priority zone. Again, we have to make sure that the panel knows that that end switch is closed, and I'm not using a zone valve on the priority, I'm using a pump. All right, so next we're showing you expanding these panels. So these are the EXP panels. So if it's an SR EXP, that means expandable. And the wiring is exactly the same. We bring the power in exactly the same. We take our thermostats and or aquastats exactly the same. We wire the circulators exactly the same. The difference is going to be on the top of the panel, we give you an expansion port. And it's going to be an A, B, and C port. So A will go from A, B will go to B, and C will go to C. One of these panels would be, it shows master on here, but we'll call that the primary panel, and the other panel will be the secondary panel. So we have a couple of dip switches on both panels. One has to be in the primary position. That would be the lead panel. The other one would be in the secondary position. That would be the secondary panel. I gave you 2 end switches coming out of the expandables. So out of my main end switch, that will go to TT on the boiler. So anything happening on either one of these panels, the actual contact to the boiler is going to come out of the primary panel. But I give you a secondary end switch for my domestic, because if it's a condensing boiler, there's generally a secondary TT on there for domestic. That would tell that boiler to high fire, and I can come out of there from my primary panel to that other TT on the boiler to make that boiler go into high fire mode. Pretty simple, very straightforward. Okay? And I do give you another option here for either another circulator, a primary loop circulator. So again, based on how you pipe those systems up, how many circulators you need to drive, you can figure that out by using these panels. Okay? All right. Now, where would we use these panels? Why would we use these panels? Well, you may do a job like this, where I'm going to do primary, secondary, and maybe I'm going to have a primary circulator on there, but I may have zone valves out there in the system, or I may have zone pumps out there on the system. So here we're showing you a primary, secondary setup where I'm going to stagger the boilers. So these boilers have their own control on here, where they're daisy chained together, and we will rotate them. They won't always fire in the same sequence. And again, our goal is to fire them only up to condensing mode. And if I need more BTUs, then we'll fire the next boiler, and so on and so forth. Here you can see there's a small indirect, because this job we probably replaced a couple of large boilers, a couple of large cast iron high temperature boilers. They're always fired in the same sequence. We killed the first one. The second one's pretty bad, and the third one was not so bad. But we changed them all. We put in condensing. We're saving them a lot of money. And instead of firing a lot of BTUs to make domestic, you know, they're probably only taking care of sinks now. This is your typical school job, or your church job, or maybe even a municipal building. And, you know, we're not feeding showers anymore, so we can have one boiler, just make domestic hot water. But maybe on the job, one of those cast iron boilers was still good because it never got a lot of run time. We can still leave that in service. So if we do need even more BTUs on some really, really cold days, and we don't want to take the other boilers out of condensing mode, then we would fire that last boiler. All right, so that's what that piping setup is all about. That's the reason for this. Yeah, you could be looking at it and saying, but Jim, you're making a radiator out of the last boiler, and you're right. But again, this would be the easiest way to pipe it up. And probably a majority of the time, that last boiler, that big old boiler that's left, would rarely fire anyway. So yeah, we're just flowing water through it, but we're barely firing it anyway. So we still made for a very efficient system. And generally what happens when we've done projects like this, after a year or two, they take that boiler out of service and maybe even replace it with a condensing boiler, okay? Or not at all. They just actually don't even need it, all right? Any questions on that? There's a lot going on there, but really everything that we've covered in our 4-week class, pumping away from the expansion tank with our air eliminators and all that kind of stuff on that main supply header still applies, whether it's residential or commercial. Okay, we talked about static pressure. What is static pressure? You know, it's the pressure of the water column in our system. And we have to make the water move through our system, and that's what our circulator does. Our circulator creates a pressure differential, but it's a closed loop system, and I got to make sure, based on the height of my system, that I have the proper pressure based at my pressure reducing valve and also at the expansion tank itself. So we gave you a chart, or we gave you the formula, right, from the water level of our boiler to the top of our heating system. Whatever that distance is, we told you to multiply it by 0.43. And then whatever that number is, add an additional 4 to it. And that's to guarantee that at the top of the system, we'll always have 4 psi. So we'll always be under pressure, even at the top of the system, which is really important because you'll have jobs where this is not occurring, and now I'm trapped with air at the top of my system. All right, so again, a very simple equation here. Take a screenshot of this. This is good to have. So you can see if it was 15 feet, all right, which is kind of typical on a 2-story and the boiler's in the basement type of home, that you'd get 15 times 0.43 gives you 6.5 psi. Adding that additional 4 to make sure I'm pressurized at the top with 4 psi gives me 11 psi. And Rob, that's why the expansion tank that I picked up at the supply house is set at 12 psi. All right, but if I've got a third story or a fourth story or a fifth story, I'm going to have to change the pressure of that tank. Plus, I'm going to have to change the pressure on my pressure reducing valve. All right, the importance of where we put the circulator. All right, if we pump away from the expansion tank is what we're showing you here. That makes the circulator work to your advantage. It's going to add positive pressure to the system. Remember, the circulator is a pressure differential creating machine. All right, high pressure has to go to low pressure. All right, so on our last couple of slides here, the Ferris wheel effect. If I make one side of the Ferris wheel move, the other side has to move, and that's the same thing with the water in our system. So if I have the pumping away from the expansion tank, what we're showing you here is with the system off, I'll have 12 psi on the suction side of the circulator, because I'm going to have 12 psi at the tank itself, the expansion tank. That's never going to change. And then now when I turn on the circulator, in this example, this circulator will be creating a 4 psi pressure differential. So now I'm going to add a positive 4 psi to the discharge side. So now coming out of the circulator, I'll have 16 psi. Since the weight of the column of water going up to the top is going to create an 8 psi pressure drop, that means at the top of my system, I will have positive pressure of 8 psi. All right, so pumping away can solve a lot of problems, some airbound systems. If you just move the circulator, that can assist you greatly. All right, if the circulator was on the return side, we're going to have to change those numbers. I'd have 12 on the discharge, okay, and I have a negative 4 on the suction side. And then at the top of my system, I would have 0 pressure. So we don't want to do that. So pump away, pump away, pump away as much as you can. All right, distribution piping. Remember, we do not care what the appliance came tapped at. I don't care if the boiler came tapped at 1 inch. It's based on the BTUs/GPM that you have to deliver in the system. All right, and how do we figure that out? We use our universal hydronics formula. So it does not matter. We have to find that flow rate. So whatever the GPM is, it's going to be based on the BTU divided by the delta T of the system. So here's a 75,421,000 job. If we're going to use a 20-degree delta, I'll divide that by 10,000. I get 7.54. We can call it 7.6 GPM. Using your pipe sizing guidelines and your Takeout Catalog, your downloads, all right, that would equate to 1-inch pipe. Okay, so this is really important. The whole reason for this training class was so you guys could equate GPM to pipe size, understand that when you're looking at the system, looking at the piping arrangement, that should then equal GPM to you, BTUs. You'll have a better understanding of what the system should be performing at, and that'll greatly help you in your troubleshooting. All right, so air eliminators. We want to use air eliminators instead of air scoops. All right, air scoops have been around forever, but there is a situation with an air scoop that I have to always be paying attention to. I have to make sure that I've got 18 inches of straight pipe in front of that air scoop. If I do not, the water doesn't calm down, and it's going to be very turbulent, and the air bubbles really won't get captured by the scoop, all right, itself, and won't get vented out of the system. We're showing you the Takeout 4900 series, all right. That will always get the air out because I don't have to worry about the 18 inches. It's got the chamber is filled up with the pole rings. It gives a lot of surface area, a lot of contact to those air bubbles. It knocks them down into micro bubbles, slices and dices them into micro bubbles. The cone shape at the top is very unique because that keeps the cone always filled with air. It's not always flooded, all right, so I don't have leakers coming out of my air separator. I do give you a shut-off valve at the top where the air comes out. You want to use these. These cost more than an air scoop. We know they do, all right? But it will save you guaranteed at least an hour of purging time. And you should be getting paid more than the cost of that air scoop per hour. So it's going to save you money, and it's going to give you a much better performing system. Next up was our circulators, and we talked a lot about the ECMs. All right, now it is on the books at the government because it was passed. We're just waiting for the government to say, okay, let it rip. So this will happen, and what this means is the AC motor circulators will eventually disappear, and we'll be dealing with the ECMs. The ECMs, these are electrical commutative motors. They're much more efficient. Using less power, they can produce more torque, more work output, and I can cover a lot of different size double O's with a single ECM. My 007E, my 0015E3 are pressure pumps. They will change their speed based on a pressure differential. The 0015E3 on the box itself will show you based on whatever speed I'm picking, how much head it can overcome or how much baseboard it can overcome. Will actually give you the footage marking on here, okay? So the box is very informative, gives you a lot of information. This particular circulator is variable speed on low and variable speed on medium. And when we put it on high speed, then it is a constant speed circulator. All right, think of this as we go into our troubleshooting, hint, hint, nod, nod, okay? When we size our circulators, we need to know two things. We need to know our GPM. So you know how we figure that out with our universal hydronics formula. But then the other thing we have to figure out is our head loss or the resistance through the system, all right? So if I'm doing a circulator with multiple zones and there's zone valves, I concentrate on the longest zone, the longest loop. If I'm going to zone with circulators, then I have to concentrate on each loop length for each zone. And what we're asking you to do is take that loop length, multiply it by 1.5, and then multiply it out by 0.04 so I don't go over 4 feet per second. Now we concentrated hard on the 100-footer because the 100-footer is worth 6 feet ahead. 100 times 1.5 times 0.04 was 6 feet. And that was for copper or black iron. If I concentrate on the 100-footer or commit that to memory, then I know a 50-footer is worth 3. I know a 25-footer is worth 1.5. Why is that important? Because just having that in my mind, all right, memorized in my mind, I can now, even when I've taken a calculator out, get kind of close exactly to what the head loss would be. So in this example, this longest loop here is going to be 150 feet. So if you knew that that a 100-foot loop was worth 6 feet, and if you cut that in half, a 50-footer is worth 3 feet, then a 150-footer, if I put those two together, should be a 9 foot of head loss. Or you can just take 150 times 1.5 times 0.04 and get 9. Any questions on that, Robbie? All right, good. So far, so good. What's important now is also knowing what type of system you're putting together, and if I am adding other components in my system, like a hydronic coil. We do a lot of hydronic coil jobs in our territory. Out in Long Island, they really like hydronic coils, especially as backup heat to forced air systems. We will see a lot of hydronic coil jobs here in our Jersey territory on a lot of radiant systems, and maybe some backup heat is going to be through a ducted system, and they'll do that off of a hydronic coil. So what we're showing you here is you do need to know the pressure drop through that coil. Very important, because in your Takeout handout, there is a page there that gives you your water conversion of PSI to feet of head. 1 PSI was equivalent to 2.31 feet of head. So in this particular example here, if I need to flow about 4.7 GPM, all right, 4.8 GPM, All right, that's 48,000 BTU. All right, so my pressure drop is around 4 point, looks like 4.7 also. We do that math, 4.6 PSI, let's call it, times 2.31, that's 10.6 feet ahead. And if you follow the arrow across, you can see, yeah, we're just under 11 feet ahead. That's important to know because that would be included with the length of piping that's going to that hydronic coil. So if I have a run of, say, 25 feet, all right, I already know that's 1.5 feet ahead, plus this 10.6, I'd add those two numbers together to get my foot of head. So now I can size the circulator properly. Very important, especially when you're using tankless water heaters when they're feeding a hydronic coil for space heating. We see that a lot in multifamily installs. Those tankless water heaters have a very high pressure drop through them. Generally, the packaged unit on the air handler side comes with a circulator, but that circulator was sized for a low pressure drop through a cast iron boiler. Once I'm taking it through a tankless water heater, that circulator is not adequate enough. It is not large enough to overcome the pressure drop of that tankless heater. We see this all the time. Robbie sees this all the time, and it's going to cause problems on the job. So that's why we're showing you a chart like this so you understand that. So once I know my GPM and head, then a pump chart like this, pump curve chart like this starts to make sense because on the bottom I read my GPM. All right, so whatever my GPM is, based on a 20-degree delta, that equates to BTUs. So, oh, geez, 8 GPM, 80,000 BTUs. My feet of head is on this side here. All right, so on that last particular project, it was about 48,000 BTUs or 4.8 GPM. So if I put a mark there, and then on the left-hand side where my foot of head is, it was about 10.6, just under 11. If I drew a line straight up and a line across, I would plot right there. And since I am below the number 6 curve, the number 6 curve would say that particular project for that air handler is going to need a 008. Okay? If you went with the number 8 curve, the number 8 curve is your 0010. I'm too low on the head side. If you went with the number 10 curve, that would be a 0012. Yeah, that would do it, but it's at the far end of the curve. We want to get as close to the center or the sweet spot of the curve as possible. All right? That's how you use a pump chart, knowing my GPM and head. Or as Johnny likes to show you, he shows you, what looks like a gun, GPM on the bottom, head on the side. All right? Any questions on that, Robbie?
No.
Oh, come on, guys. Keep Robbie engaged here. All right, so here we're showing you our 007E, the features and bennies. It's got the light to show you that, yes, it's powered, and yes, it's functioning. The orange light tells you if it's functioning properly. If you see a white light, it's trying to purge its air. All right, that's the air purge mode. It'll flash white. It'll speed up to high speed, and it'll do this up to 100 times to get the air out of the volute. If you see a red flashing light, the circulator got seized up because there's just sludge in the system, and it's going to rock to unblock itself. And then if it goes to a solid red light, it turned itself off so it doesn't burn up, and it's waiting for you to clean itself up, to get out there and clean it up. All right. The bio barrier is going to protect it from the magnetite or that sludge that's in the system. So a mag dirt separator really is not needed with these circulators. But again, if I'm putting it in an older system that's probably got a lot of sludge in there, all right, you may want to treat that system. There's no programming required here. So this is a variable speed circulator right out of the box. There is no ground wire because it is a composite body, so it's just 2 wires. Flow check comes in the box, so you can use the flow check or not, and that would go on the discharge side of the circulator. So what's the difference? This is my standard AC 007 pump curve, long flat curve. That's why it works so well in our standard cast iron boiler systems. The difference here is the 007E curve holds 10 feet of head out to 8.25 GPM. So right down about right there, 8.25 GPM. 8.25 in a 20-degree delta system is 82,500 BTUs. So that's a pretty good sized house. So as the zones would open and close, if it's a zone valve system, they will follow this 10 foot of headline. So let's say I have 4 zones and I'm going to and I need to move 70,000 BTUs, 7 GPM. I will run here. And as the zones open and close, I will go back and forth across this 10 foot of headline. Okay, so that's a good thing. That makes our system more reactive and more efficient. It gets us closer to our actual system curve. It's not gonna nail it, but it'll get closer to our system curve and make for a better system. And we consider that area the sweet spot of the curve because we're basically in the center of the curve. The 0015E3 has the same characteristics as the 7. All right, the same sure start, air purge, biobarrier, auto unblocking, IFC, the same lights, but you get 3 speeds. And I'm variable speed on low, I'm variable speed on medium, and I'm at full speed on high. So that pump curve looks slightly different. So on the low side, I'll hold 5 feet ahead all the way out to 12 GPM or 120,000 BTUs at a 20-degree delta. If I put it at medium speed, it's the 8.25 at variable, same curve as the 007E. And then if I go into high speed, now I'm at single speed here, and I just follow the curve as zones open and close. In both medium and low, as I'm changing speed, I'm also changing the amount of power that we're pulling. So both of these circulators at max speed are only 44 watts. Your standard 007 is an 80 watt. So I'm half the wattage, all right? And as I go into variable speeds and I slow down, I actually pull less voltage, okay? 0015E3, great service pump to have on the job as a single circulator or even as a zone pump circulator. Then what we came up with is the VT2218, another variable speed circulator, but this is a delta T circulator. This pump is going to come with 2 thermistors. I'm going to measure my outgoing temperature. I'm going to measure my return temperature. And the circulator, based on whatever delta T you want, you program in, will maintain that delta T as zones open and close. It will work within this whole green band, okay? And if I need to move 6, say at 6 GPM at 6 feet ahead for, say, 3 zones, as the zones open and close, it will change its speed and basically match the actual system curve that you need. So this circulator will create new pump curves as zones open and close. Okay? Really makes a better performing system, much more comfortable system, because now my circulator basically is matching the heat loss of the building. So especially on a condensing boiler system, as the boiler will change its output based on the heat loss and the temperature outside, now my circulator will react also. It'll always maintain whatever delta you want. It doesn't care about the water supply temperature. All it cares about is maintaining that delta T that you want. All right, so that's a big deal. This is what I have on my system, and my system's cast iron, and it still has made a big deal, especially in the comfort level. Okay, so it comes out of the box set at a 20. You can set it from a 5, I believe, up to a 50-degree delta. So what's going to happen is my ECMs, as you can see, we're overlapping their pump curves on my standard double O chart. I can replace multiple double O's with 1 or 2 of my ECM circulators. That's where we're going with this, and that's what eventually is going to happen. Now, with the variable speed circulators, especially the delta T one, if I can match the actual system curve, that's going to make for a much better performing system. And the system curve is basically the thumbprint of the system, okay? Meaning I could have a 100,000 BTU job, 4 zones on the house on one side of the street, and the other side have the same 100,000 BTU 4 zone system on the other side of the street, but they can each have a different system curve because I may have different loop lengths. So when we pick a circulator, we always want to be as close to a pump curve as possible. So on this particular example here, we are showing you a 7 GPM at about 9 feet of head. So we put our dot there, and we are going to use this circulator because that pump curve is very close to our system curve. But what ends up happening is we have to follow the pump curve if it's a single speed circulator. So here in this application, when all the zones call, we actually end up over pumping by a bit. All right, we're going to 9 GPM here, and instead of being at 9 feet ahead, I'm probably at 11 feet ahead. So I'm over pumping. So what does that mean to my system performance? My delta T gets squeezed down. So by over pumping, just by this 2 GPM here, and squeezing down the delta T, on the coldest day of the year, not such a big deal. But when we start getting warmer and warmer outside, we get to that 55-degree day. It's May, and I woke up this morning and it was 54 degrees outside. If I still had my heating system on, it would have been running, okay? And now if a single speed circulator was there, I would be over pumping dramatically, and my delta T would get squeezed down probably to single digits. This is where we run into the problem. So with today's technology, especially with the delta T circulator, I can match the curve as needed, and I have better system performance and better comfort. Okay, our review is over. It is time for you guys to start troubleshooting. All right, so at this point now in the presentation, we're giving you problems, and you need to use all the information that we've given you, use the handouts that you've downloaded to figure out what's going on. So here's a job, the moose antler piping job. This is a primary, secondary job. And I got a problem here. There's not enough heat. I'm giving you a boiler size. I'm giving you pipe sizes. I'm also giving you the GPM for all the zones. So, ladies and gentlemen, there's not enough heat. So I need you to look at this using all the different techniques we've given you and tell me what's going on. I have to give you a few minutes here, so I'm going to stop talking and just stare into the camera. As Rob whistles. What's happening here in the system? Anybody yet? It's going to take a bit of time. So I'll give you a clue.
I got one answer here.
Oh, cool. What's the answer?
Header size is too small.
Header size is too small. Well, yeah, based on 140,000 BTU boiler at a 20-degree delta, that would be 14 GPM. Yeah, that's a stretch for 1-inch pipe. But remember, they're saying that there's not enough heat.
Need 1.25 inch header. That's the second one that just came in.
I'll give you a hint. Look at your GPM and compare it to the boiler BTU. Anybody catch that yet?
Boiler size is too small.
All right, so the gentleman who said the boiler size is too small, how did you determine that the boiler size was too small? And please don't tell me, well, he said there wasn't enough heat. No. Give me a reason why. My man Brett in the back's got the answer. And he's a marketing guy. Come on. You guys are the professionals. You're the heating professionals. Tell me what's going on here.
18 GPM is 180,000 BTU.
Well, it's not 18 GPM. 2.5 and 2.5 is 5. So there's 5, there's 10, there's 15. It's 17.5, right? GPM, that's 175,000 BTU. So, all right, excellent. All right, we're thinking. So my GPM that I'm sending out to my system is equal to 175,000 BTU. So yeah, my pipe sizes aren't going to be right, but the boiler is 140,000 BTU. Well, there's a big difference. It's 35,000 BTU difference. How are we going to figure this out? What is the ultimate? How are we going to figure this out? Robbie, do you know how we're going to figure this out?
Do I know how
Yeah,
to
you.
figure this out?
Put you on the spot. Do you know how you're going to figure this out?
Well, first we need to figure out, what our actual load is as far as the house is concerned, how much baseboard we have.
There you go. So he's got it. So we were heading down that road. So if I'm trying to move 175,000, but I only got 140,000, and I'm telling you there's not enough heat, well, one of those numbers is not right. I got to do a heat loss. Okay? So I could be over pumping, all right, squeezing down the delta, or I could have an undersized boiler. So I got to do a heat loss. And if the boiler was undersized and it is that 175,000 I have to deliver, then yes, that piping has to be replaced. All right. Plus, even if it was 140,000, again, the piping has to be replaced. All right. Very good. All right. Next problem is going to be a little harder. You're going to have to draw this out, or you may want to take a screenshot of the drawing that I'll put up after this. So this is kind of one of those problems from grade school when the train leaves New York at 1 o'clock and the other train leaves Chicago at 1 o'clock. When do they pass? Chris always knows that answer. She's really smart. So here I got a cast iron boiler. It's 80,000 BTU. I've got a domestic load of 80,000 BTUs, 4 zones at 2 GPM each. I got a pressure drop of 3 feet of head at the boiler. I got 6 feet of head at my domestic tank. And my system, my space heating side, has got a pressure drop of feet of head of 6 feet. We need to size the boiler/system circulator. We got to size the DHW circulator. I got to figure out my piping size for my boiler, my supply and return manifold pipe size, the zone pipe size, and the domestic hot water pipe size.
So just going back to that last example.
Yes, sir.
Question was, can we raise the water temperature, obviously after checking the load?
Well, I mean, if it's a dead of winter and you got to get them through it, you can do that. You could do that, if the boiler can handle that type of temperature, but that's not a permanent fix. Not a permanent fix, all right? Because there could be other issues on the job. I may not even have enough baseboard. So actually, that was a great question. Sometimes you have a job and you're going to replace the boiler. One thing you ought to check, especially if it's cast iron, is, what was that aquastat setting at? Because if it's sitting there at 200 or 220, that could be a case where they undersized the boiler because they sent in higher water temperature. So if we don't check that and just assume that it was 180, you can get caught with your pants down there. That can cause you a problem. All right, so let's get back to this job. So if you can take a screenshot of this or draw this out quickly, I got an 80,000 BTU boiler, 80,000 domestic load. I need to size the circulator for the boiler and the system, okay? And there was, what was the head loss on the boiler side? We had 3 feet and 6 on the system, and I've got 6 at the domestic, okay? So we need to size the piping and the circulator for the boiler. We need to size the piping and the circulator for the domestic. And we need to size the supply and return header and each loop for the space heating. All right, and it was 2 GPM per loop. So let's see if we have some high achievers out there that can put that together for us. So it's a 20-degree delta T. I failed to mention that, but nobody asked either. Shame on you. 20-degree delta T. So how about we go step by step? What would be the GPM required for the boiler at a 20-degree delta? Type that in, let Robbie know. Nope, no takers on that one? Oh, come on now.
It's an easy one.
That's an easy one.
There we go, we got it. 8.
All right, so we got 8 GPM for the boiler. All right, I got an 80,000 BTU for the domestic. It should also be 8. All right, so now that I know it's 8 GPM, what should be my pipe size based on your pipe charts? Based on 8 GPM. Anybody?
1 inch.
We got 1 inch. 1 inch is what we should have coming out of our boiler. 1 inch is what we should have going to our indirect. 1 inch should be our supply and return header, because the supply and return header has to have all the BTUs. Each zone was 2 GPM. What size should your zone piping be? Brett's looking it up. He's going to have the answer before you guys will. Come on now. Come on, he's a marketing guy. You got to be faster than him.
You got it, 3/4.
3/4 pipe. It's only 2 GPM, all right? 3/4 pipe would be adequate. Now, we got to size the circulator now. So 8 GPM, and I had 3 feet of drop at the boiler and 6 feet through the system. That's 9 feet of head. So 8 GPM, 9 feet ahead. What circulator would you be picking? So I'm kind of pushing you along here by putting up this pump curve.
All right, so we have one answer here, a 007E.
Yep, 007E would be fine. 8 GPM is right at the spot as we would be starting to go out of variable speed, and it can hold 10 feet ahead, so a 007E would be an excellent choice. 8 GPM, anybody want to look at their 007 curve? Standard 007, if you happen to have that. 8 GPM at 9 feet of head. Still sits. No, it actually goes above the 007 curve. It actually would have to be a 0010. So here's an advantage of what the 007E can do for you. It'll hold a higher pressure, can overcome a higher resistance for longer versus a 007. So 007E would be the circulator for our boiler system and also for our domestic, because it's the same GPM and same head. All right, very good, very good. All right, next off, condensing boiler, priority domestic hot water, primary, secondary piping. So this is what it's going to look like. So if you want to jot this down, make a quick sketch. All right, so I've got my closely spaced T's, so I've got my flow rate for my boiler. I've got a circulator just for the space heating. All right, so here's my closely spaced T's. So this is my boiler loop. Here is my system loop. And then I've got direct hot water coming off the domestic hot water. Okay, that's the flow that we got going on here. So if you can quickly draw that out, I'll let you know what's going on and you can answer all the questions. So if you've drawn that, here's what's going on in the system. The boiler is 100,000 BTUs. The domestic load is 150,000 BTUs. So this is already installed, guys. It's not like you got a choice here. Okay? Each zone is worth just under 2.5 GPM each. The boiler head is 12 feet. The domestic head is 6 feet. The system head is 9 feet. We got to size the boiler circulator, the system circulator, the domestic circulator, what size piping for my boiler, what size piping for my supply and return, what size for my zone piping, and what size for my domestic hot water. So, I threw a left turn at you here. So again, I'm going to see if I can lead you down the path. Your boiler is 100,000, your domestic load's 150. Okay, let's see what you guys come up with. This will take some thinking. Nobody asked me to delta, so we'll say 20-degree delta. 20-degree delta. So let's figure out what our GPM is for our boiler. So at a 20-degree delta, 100,000, type into Rob and tell him the GPM for the boiler. Any takers yet, Robbie?
I have one that says 10.
All right, great. So now we know there's 10 GPM for the boiler, and I know I have to overcome 12 feet ahead. So the size that boiler circulator, I got to move 10 GPM, 12 feet ahead. You're going to go to your 00 charts. All right? 10 GPM, 12 feet ahead. That will be a 0012. Okay? That's the best selection at 10 and 12. It sits right underneath the number 10 curve, which happens to be a 0012. So what was the caveat here? What was the trick? The domestic hot water load is 150,000. You have a 100,000 BTU boiler. What is the GPM that you will deliver for the domestic load? Please type that in. Rob's doing a dance. I think somebody got it.
Not yet.
Not yet.
No. One gentleman says 10.
Nice. That gentleman got it because that's all the boiler's going to produce. Even though the domestic load's 150, the boiler's only giving you 100,000. So it's 10 GPM for the domestic. All right. So the head loss through the coil on the indirect is 6 feet. But I do have the head loss through the boiler because remember, guys, it's direct hot water. All right, this circulator, this circulator's got to pull through the boiler, then through the coil, and through the piping here. So the piping won't be much, but I got a pretty good head loss at the boiler. So I got to put that 6 feet ahead and the 12 feet ahead together. That's 18 feet ahead. So 10 and 18, look at your 00 chart. 10 and 18, where is that going to bring us? That is going to bring us to a 0011. All right, very good. System is 9 feet ahead. What's the GPM on the system side? That's the circulator at the top. My man who got the boiler GPM and the domestic GPM should be nailing the system GPM. Anything, Robert?
Not yet.
No? Well, we got to move things along. That's going to be 10 GPM, guys, because again, the boiler's making 100,000. We're going with a 20-degree delta. So 10 GPM, 9 feet ahead, looking at the 00 chart, that's going to be a 0010. Looking at your piping charts, 10 GPM, okay? Guys, what's going to be my pipe size based on 10 GPM? It's going to be 1.25 inch pipe. So any place I got to move 10 GPM is going to be 1.25 inch pipe. All right, my zone piping, it was like 2.5 GPM per loop. Again, 3/4 pipe. Bonus question. How many circulators have to run when I make space heating? When there's a call for heat, one of those zone valves opens, how many circulators have to, Rob is doing a dance. How many circulators have to run? Quickly type in that answer for me, please.
I got 2 answers here. I got a 1 and a 2.
The answer is 2 because the circulator for the boiler has to be firing because I need to make flow here because it's primary, secondary. So the boiler has to inject BTUs into the system side, and then the system circulator's got to make the flow go that way. All right, pop quiz. How many circulators run for domestic hot water? Type that answer in.
1. I got
Nice.
3 ones.
Nice, because what'll happen here, since it's going to be prioritized with my ZVC controller, these 2 circulators will be off and only the domestic will run, and that's what's going to pull through the boiler, through the coil, and back. Excellent, excellent. So using our 00 chart, because these GPMs were pretty high, we went with the standard 00 series, all right? Okay. Moving on, one of the other things that we consider very much in our designs of systems is when do I go with a zone pump system? When do I go with a zone valve system? So our great minds here at the world corporate headquarters of Wales Darby said, you know what? If my system is 130,000 BTUs and less, we consider this a zone valve job. Okay? And then if my system is 130,000 BTUs and greater, we consider that a zone pump job. Let me give you an example, or you guys are going to figure this out for me. All right? So here's 2 different heating systems. Let's concentrate on the 85,000 BTU system. So the 85,000 BTU systems, you can see I got 3 zones. This is a 20-degree delta system. Please type in and tell Rob what the GPM is for the boiler based on a 20-degree delta.
All right, they're coming in. 8.5.
8.5, perfect. Since this is an 85,000 BTU system, I'm considering this a zone valve system, and that would then tell you all you have to do is concentrate on the longest loop. So my 3rd zone's the longest loop. It's 137 feet. What would be the head loss for that loop? Please type that in and let Robbie know.
Uh, 8.22.
8.22, all right, a little bit over 8 feet ahead. Excellent. So that means I would size the circulator just for that longest loop, all right? All the BTUs for all the zones, but if I can overcome the resistance for the longest loop, I'm in good shape. 8.5, 8.22, hey, that's a 007E. That's a 0015 on medium. There you go, VT2218, easy. Now look at the larger job, 175,000 BTUs, 5 zones. Another 20 degrees delta T system. All right, tell Robbie what the GPM is on this job. Should be easy. They should be flying in.
17.5.
17.5, great. If this was going to be a zone valve system, you'd have to concentrate on that longest loop of 151 feet. Well, we already know that a 6-foot loop is 100 100-foot copper loop would be 6 feet ahead. All right, so if I cut that in half, we know 50 is worth 3, so it's going to be slightly over 9 feet of head. So 17.5 GPM is a lot of GPM at 9 feet ahead. It's a good sized circulator. What would be the problem if it was a single circulator? That one zone coils, the first zone, only 62 feet. To save time, that's only 3.72 feet of head, just under 4 feet ahead. I would be dramatically over pumping if I just use a single circulator here, okay? So to me, this is a zone pump job. So if you broke it down zone by zone, well, I didn't give you the GPM per zone, but if you just divided the 175 by 5, it'd be 35,000 BTUs per zone. If you want to check me, do the math. So with that being said, that's 3.5 GPM per zone. So again, for the first zone, I already told you it's 3.72 feet ahead, okay? Second zone at 89 feet, that's only a little over 5 feet ahead. The 102, you know, a 100-foot loop is worth 6 feet ahead, so that's slightly over 6 feet ahead. And the 122 loop, that's 7.32 feet ahead, and we already did the 150 at 9 feet ahead. So what circulator would I be using, or circulators, okay? So here's a 00 chart. If I was going with, let me see, I wrote this down. Where are we here? Yeah, so if I'm using 3.5, it's at 3.7 feet ahead, I'm down here. That would be a 006. You guys are not going to use a 006. If I'm at 5.43 feet of head, again at 3.5 GPM, I'm down along here. That's going to be underneath the number 3 curve. Again, that's not going to be a pump you're going to use. You're going to be using all these different smaller 00s. That'll cost you much, much more money. All right. If I go to the 0015 E3, all right, and I do 3.5 GPM, boom, right there at 3.7, oh my gosh, that's going to be at low. If it's going to be just over 5 for the next zone, I could live dangerously and put it right at low because it'll hold 5 feet ahead. The 102-foot loop is 6.12. I could live dangerously and keep it at low. It would just open up my delta slightly on the coldest day of the year, or set it at medium. On the 4th zone where it's 7.32, now I do have to set it at medium. And the last one where it's 9 feet ahead, I'd set it at medium. So I could use a 0015 E3, and 3 out of the 5 zones will all be set at low. And I'd be much, much closer to the actual curve per zone, system curve per zone. So that one circulator would save you a lot of time, effort, and money in setting up that system for proper performance. All right, really quick here, static pressure. Here's the particulars on this job. Is it correct? All right, is the pipe size correct? Is the circulator size correct? Is the system working pressure correct? How about we start from the bottom up? System working pressure. We're telling you it's 16 PSI. You got 41 feet from the water line of the boiler to the top of the system. What should be the system pressure? Do you know, Robbie? Come on, math it out. Click, click, click. Let's go. See, Rob does this in his head.
Yes, I don't write anything down.
Are you an idiot savant? No, I qualify as idiot. You could be the savant. Well, 41 times 0.43 plus 4 should equal 21.63 psi. So the psi on this job is wrong. You'd have to take that expansion tank off and pump it up and set your fill valve to that 26 and change psi, 26.63. All right. You've got your circulator at a VT 2218. Your total equivalent length, your longest loop is 145 feet. What would be that head loss? 145 times 1.5 times 0.04 should equal. What are you getting there, Rob? What are they typing in?
I don't have any answers yet. 8.7?
8.7. So I have to move 10 GPM on a 20-degree delta T at 8.7. The VT 2218, if you're looking at that curve, not a problem. We're in good shape there. Pipe size, I'm trying to move 10 GPM, 1-inch pipe. Come on, everybody should be jumping on this one. We're getting no's across the board.
I'm not getting any answers
Oh,
yet.
come on now.
That was my answer.
That was your answer?
I got 1.25 inches.
1.25 inches.
Yep.
Excellent, excellent. All right. We're moving along here. All right. We're moving along here. So here we're looking at this particular job. All right. It's a 20-degree delta. It's 90,000 BTUs. That's 9 GPM. Boiler pipe size, we just went through this. All right. 9 GPM. It could be 1 inch. 1.25 inches would make me happier here. This particular job, I really want to spend the last few minutes on, because this will really show me if everybody's been really absorbing all the information. I got a problem on this job, all right? My problem on this job is I run out of hot water, and one of my space heating zones doesn't heat adequately when it gets really, really cold outside. So you can see the BTU of the boiler. You can see the BTU required for the indirect, and you can see my boiler header piping size. So the piping size for the boiler is 1.25 inches, and my supply and return header is 1.25 inches. The space heating load's 115,000 BTUs, 20-degree delta system, okay? So immediately you guys should look at this and say, okay, I need 13 GPM for the boiler. 13 GPM for the boiler. I'm not asking you to pick a circulator. Is the piping size right? So it's either a yes or a no.
The boiler piping?
Boiler piping. We're telling you that it's 1.25 inch piping. Are we getting yeses across the board? We're getting nothing.
Again, nothing.
Come on, Chris can tell me if the boiler pipe size is right.
I got a no.
For 13 GPM, 1.25 inch pipe can handle up to 14. So yes, that pipe size is correct. Since my boiler is going to be making 130,000 BTUs, and that would be 13 GPM, my supply and return piping at 1.25 inches would be fine, okay? The space heating load's 115,000. That would be 11.5. That's still going to be 1.25 inch piping, okay? Now, the indirect is 135,000 load, but I'm only going to be giving it 130 because that's what the boiler can produce. That's going to be 13 GPM, all right? So that's going to need 1.25 inch pipe, but they're running out of hot water. They're running out of hot water. What's the fix? What's going to be the fix? They're running out of hot water. So yeah, I already told you the piping is wrong. We got to repipe it. Well, what else do we have to do for the hot water? I don't know, Rob, there's a zone valve on that. Those are standard Honeywell zone valves, 3/4 Honeywells.
This goes back to like week 2.
This goes back, but it goes back. CV rating. Oh, Jim's giving you the answers. CV rating. Anybody? Bueller?
Well, I got 2 answers here, but neither of them got it. Not enough heat emitters and prioritized.
Well, okay. Yeah, we're going to prioritize it. That's a no-brainer. But what's the big problem here? We're trying to move 13 GPM through 1-inch pipe, so we know that's wrong. But we're also trying to move 13 GPM through a standard 3/4 Honeywell zone valve. All right? If you were, keeping notes, that 3/4 zone valve from Honeywell is a 3.5 CV, or 35,000 BTU valve. And you're trying to move 130,000 through it. It's too small. So some guys generally, when we do this live, they say, well, I'll go with the full port 1-inch. Well, that's only an 8. That's only an 80,000. So you really need to use a circulator, and you really need to change the piping and take the indirect directly off here, direct hot water. So we'll have a circulator, and you're going to cut into the boiler loop and do direct hot water this way. So that circulator will pull through the boiler and into the indirect. That's your proper fix right there. The other problem is you've got the one zone, you got a one space heating zone that needs 4 GPM, and that's the zone that underheats. What's your fix there, guys? And it's got a 3/4 Honeywell zone valve on it. What's your fix? First off, tell me how many BTUs that zone actually needs. Turn those GPMs into BTUs. Anything, Robert?
40,000.
40,000. So I'm trying to move 40,000 through a 35,000 BTU valve. I'm 5,000 BTU short. I'm a half a GPM short. Easy fix is take ozone Century. If it's a press, it's a 9.5. That's 95,000. If it was sweater thread, it's a 10.3 or 103,000 BTUs. Okay? These type of things come up all the time. That's why we give you these examples. These are jobs that we have seen, and these are the problems that occurred, and these are the fixes. So we have to use all the tools that we gave you. Use the universal hydronics formula, use the head loss formula, convert BTUs to GPM and GPM into BTUs. Always make sure you got the proper pipe size. Always make sure you can flow the proper GPM through your valves, all right? Always, always, always look at how it is set up to find out your answers. We don't want you to be guys like this. These jobs are out there, and that is not something we just found on the internet just because. That's a job we actually saw within our territory, all right? And we also, now this one we did find on the internet, but this one still blows my mind because that guy was satisfied and actually put out his hand looking for his payment, all right? So we don't want you to be these guys. Use the tools that we gave you. It's the same formulas over and over again. Universal hydronics formula, your pipe sizes, your head loss, all right? Get comfortable doing heat loss or get a partner that can help you do the heat losses, and that partner would be your wholesalers, or partner up with us as your manufacturer's rep here at Wales Darby. So that wraps up our advanced 4-week hydronics series. Number one, thank you for hanging with us for these 4 weeks. All right, this is one of the most fun webinars and live classes that we do, so I really do appreciate your time. Chris and Rob, thank you very much. We're going to be taking a break. Our next class or our next webinar is going to be June 8th. All right, so we're taking a break on the Memorial Day coming up because some of you guys are going to be disappearing for vacation before and after. So we're back on June 8th. That's going to be a space pack, small duct, high velocity air conditioning class. Tune in for that. I'm getting constant calls on space pack. You need to take that class if you're going to be dabbling with space pack. So again, thank you very much. Any questions, please email me at jdepalma@walesdarby.com or John Resso at resso@walesdarby.com, R. Clemens at walesdarby.com. Chris, should I give out your email? No, I guess not. All right, any questions at all, please contact us. And again, thank you very much for your time. Greatly appreciated.